Hello, physics class. We are going to continue in our discussion on electricity and talk more about this electron movement and stuff like that. Today, one of the things that we're going to talk about is called charging. Okay, there's two ways that we can charge an uncharged object. Okay, one is through what we call conduction, and this is when surfaces come into direct contact with each other. And another way is by induction. And that is when the charging happens without direct contact. Okay, now charging by conduction is pretty should be pretty natural to us. Like when we scuff our feet on the carpet, we are causing friction and we are pulling negative electrons out of that carpet and into our body. And then when we touch the doorknob or another person, those electrons leave us and we get a little spark because of the sudden uh, motion of those electrons and that electricity. Okay, that's conduction though, right? You could do this with your comb in your hair. I don't know if you have a wool blanket in the winter and you sometimes you're kind of cold, and so you rub your legs back and forth under your blanket and it's dark, and so if you kind of look under there while you do that, you should be able to see some sparks flying because you're charging different parts of that blanket with the friction, and then it's touching parts of your body and creating a spark. Now this is something that we aren't very used to, but probably happened, you probably talked to your grandparents about it, but seats in cars used to be plastic, right? Like in 1950s cars, they used to be plastic and they used to be long benches. And so if you slid around on those, you could actually create a charge with that friction and things like that, right? We know that clothes in a clothes dryer get charged, right? Unless you put what's it called, dryer sheet in there, right? To attract, the dryer sheet actually attracts the charge, and so you don't get static, quote unquote, static cling between your clothes. So all of those are examples of conduction, right? We're charging by contact. All right. So for example, if a negatively charged rod is placed in contact with a neutral object, right, some of the electrons will move to the neutral object, right? Now, let me kind of draw this for you a little bit. So let's say that you have a rod, okay, a glass rod, and it has a bunch of negative charges on it. Okay. And you put it into contact with a sphere, right? So that's neutral, right? It's got positives and negatives and stuff, right? It's got positives spread out. Oh my gosh, not doing well here. Um, it's got negatives, right? But as soon as this charged rod comes into contact, not only do some of the uh, electrons move into that, let's take a look at the sphere now, because of the negative of the rod, it's actually going to push the other negatives to this side, and it's going to actually put the positives more on this side until that rod is moved away, and then they'll balance out again and they'll spread out. But as long as that rod's in contact, we know that like charges repulse and the opposite charges attract, and so we get this. So this would be charging by conduction, and we actually would have more negatives. This would be a negatively charged particle or object because it has more electrons on it now than it does protons or positives. And so we get a charged object. Okay. Now, charging by induction is a little bit more complicated. Well, it's not really much more complicated, but there's certainly some more steps. Okay. So let's say that we have two spheres. Oh my goodness, that's awful. Let me try that again. Sorry, when I use Zoom, I can't use my pen on my laptop, so I have to use my finger. So let's say that this is sphere A and this is sphere B. Okay. Now, Sphere A and B, these are supposed to be touching each other, okay? They are touching each other, but they have no charge right now, right? They have an equal number of protons and electrons. That's what no charge means, right? Okay, so now what we're gonna do, that's part A. Let's see if oh good, I made them touch this time. Okay, and so now if we put that charged rod near it, right, and this has negatives in it, okay, what's it gonna do? Well, it's gonna push all the negatives into sphere B. And it's going to attract, I'm gonna make these green this time. It's gonna attract all the positives to this side, okay? So now what? Well, now if we were to separate sphere A and sphere B with this rod close to it, what happens? Well, now B has a bunch of negatives. It's a very negative sphere. And sphere A is a very positive sphere. And so we have charged both sphere A and sphere B by putting this negative rod just near it. They don't have to touch because we don't want electrons to jump from the rod to the spheres, right? We just want to realign them so that when we separate these two spheres, B is negatively charged and A is positively charged. So this is what it means to charge by induction. We are moving electrons, okay, from one place to another. All right. So now all the electrons are in sphere B and sphere A is very short on electrons, okay? Now you can actually do this with just a single, well, I don't want to say single. We can still charge by induction. Let's say we have a single sphere, right? And it's got negatives and it has positives. Okay. Now, if we put a negatively charged rod next to it, again, okay, what's going to happen? Well, it's going to change the alignment of things, right? All the positives, oops, sorry, I got to keep my colors straight here. All the positives are going to move to this side of the sphere, and all the negatives are going to be repelled over to this side of the sphere by just putting this thing close to it. Now, here's what's kind of cool. This is charging by induction, but we're going to use our body to also help out. Now, if we were to touch this sphere right here with our finger, okay, what do you think is going to happen? Right? What we've done is we've now given those electrons a path or a place to flow to the ground because the ground is a huge reservoir for electric charge. This is what is meant by grounding, right? So when we touch this and we're standing on the ground, we're going to allow negatives, right, to flow, right, down our hand and into the ground. Well, what happens is now my sphere is what? Now my sphere is left with positives. My spheres stink on this thing, but you get the idea, right? My sphere is now left with positives, right? And not only that, I should have drawn it a little differently because we're going to keep this rod nearby. And so our positives are here, and we're still going to have our negatively charged rod nearby. Okay. Now, what's going to happen is now, since all those negatives left, now the attraction force, okay, let me back up. In this, in this sphere right here, when that rod is close by, there might be some attraction between the positives and the negatively charged rod, but there's also a little bit of repulsion because of the negatives, right? But the positives are closer, and because the inverse square law, they're going to win. And so this thing's going to lean a little bit to the right. But now that all the negatives are gone, back in this third picture here, now that sphere is going to actually move closer to the rod and actually touch it. Okay. And what happens is a lot of these negatives that were in the rod are actually going to flow into the the ball, the sphere, right? And so now what we're going to have is we're going to have a sphere that now has a lot of negatives in it. Still going to have some positives, all right? But now it's going to become negatively charged. So it was positively charged here, right? But now it's going to be negatively charged here because it came into contact. So we went from charging by induction and then allowing the electrons to flow to the ground. And then we got contact at this point right here, okay? And we actually charged it by conduction there. This is actually the theory behind a lightning rod. You know, we talked about Ben Franklin a little bit the other day, and he kind of he figured this out. So the way a lightning rod is made, right? It's a long rod, obviously, but it comes to a point. And the reason it comes to a point is because we want charge to leave that lightning rod at that point. Okay. And the reason this is okay, so now I got to talk about lightning. All right. All right. This is my cloud drawing. Ooh, that's nice. Um, lightning, we usually find lightning where there's warm air because as warm air is evaporating up into the sky and it's as it starts to cool, it comes into contact with crystals, ice crystals up in the upper parts of the atmosphere. And that friction creates some electricity, some electrical charge because of conduction, right? And so what happens is you actually get negative, these warm air molecules, I'm sorry, uh, these warm air molecules are moving up, right? And the negatives end up at the top, I'm sorry, at the bottom of the cloud, right? And the positives end up at the top of the cloud. And they are obviously repelled, okay? And if enough charge builds up in this cloud, we might get lightning to lightning, I mean, cloud to cloud lightning here. But what happens is on the ground, right? The positives on the ground start to get pulled up, right? And now you've heard people say that lightning actually goes from the ground up. That's not entirely true, but it kind of is because the negatives in the clouds, if the clouds are really low, they're going to start pulling on those positives on the ground. And so what a lightning rod does is it allows those positives to slowly be pulled up and to leave the rod. Like they want them to go off slowly though. That's why it comes to a point because then it can't hold as much charge. And so it's just going to slowly leak off positive charges into the air because what lightning is when there's a big buildup on the of a tree or a building, right? When you get a massive concentration of positives all over the place, right? Now, all of a sudden, that the attraction strength because of our electrical force, Coulomb's law thing, the force of attraction is too great, and that those charges just leave in a hurry, right? They take off, and that sudden burst of speed creates so much friction that we get lightning, okay, and then thunder. Okay, so a lightning rod actually is trying not to attract lightning. It's actually trying to let those positives off slowly so that we don't get lightning. Now, the other hope is that if it can't avoid that, right, if there's too much charge let off, that the lightning bolt will go into the lightning rod and then into the ground. Okay, but a lightning rod is there to slowly let off positive charge so as to avoid lightning. Okay. So that's kind of how lightning and thunder work in a very short explanation. Okay. Now there's one other thing that goes with this, and we're going to talk about the whole balloon rubbing it on your head a little bit. Okay. And we're going to talk about polarization. So polarization is kind of like charging, but a little bit different. That's a nice drawing, I know. Okay. Charging by conduction only works if you're working with conductors, right? With a good electrical conductor, okay? But when a charged rod is brought near an insulator, Well, there's no movement of electrons, right? There's no free electrons that can move through the insulating material. So what does happen is you do still get a rearrangement of charges within that object or the atom or the molecule or whatever. Okay, so even though the electrons themselves may not move, there is a kind of a realignment. All right, and so think of it this way: we have in an atom, let's just say, or molecule or whatever, right? The I don't know how to draw this very well, but I'll just draw a sphere. Most of the electrical of the negative charge is going to be kind of center, spread out along this area here, and the positive charge is going to be kind of focused in the middle, right? But because of repulsion and attraction, this is the way it's going to happen. Okay, but if we bring a negative rod, let's say a charged rod, okay, then let's say that we bring it and we put it over here, right? So this is a negative rod. I got my colors mixed up this time, sorry, right? What's going to happen though is this positive part of the molecule or the group or whatever is going to be slightly pulled towards that negative rod. And the negatives are going to kind of be repulsed in the other direction. And so what we have within the object is we get a rearrangement of things. We kind of get that center, that positive that was in the center is now going to be off to the right a little bit. And the negative, there's going to be kind of a negative center that's kind of being repulsed a little bit. And so the atom or the molecule kind of starts to move so that there's more positive on one side and more negative on the other side. Okay, and this is actually what happens. This is why molecules of water stick together. Let me draw it a little differently. Let's say that we have a bunch of water molecules. Okay. Okay, these water molecules are all, they actually have a slightly negative charge, but that doesn't really matter. So when we bring a negatively charged rod, right, here's some negatives. When we bring a negatively charged rod close to this, what happens is the positives start to move in this direction. They line up so that the positive part of the atom is over here on the left side, and the negative part of the molecule is on this side, and they line up, and they kind of link together because of this, and actually forms what we call hydrogen bonding in water. Okay, so it's not, we're not moving any electrons, we're just realigning electrons, and that's what polarization is. Okay, charging means electrons are actually moving from one object to another. Okay, now just to kind of sum this up for today, you could take a comb, for example, that has a lot of positives, right? Because comb is plastic, and so if you rub it, you can create a charge on it, right? So you could try this. If you took a plastic comb and little bits of paper, you could actually, those little bits of paper are going to become polarized, and the negative part of the paper is going to actually jump towards the comb. So if you were to put a comb through your hair a bunch, blah, 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 and then you could just put that comb now next to a little, I'm talking like a little itty bitty piece of paper, it'll actually pick it up without touching it, right? Because the negative side of that paper is going to be attracted, right? So let's just say our little piece of paper is like this, and the negatives are over here, and the positives are over here, and the comb is over here. Okay, I'm not going to try to draw a comb, right? But it's positive. So according to the inverse square law, the negatives win, right? Because that distance is closer than that distance. So yes, there's a repulsive action here and an attractive action here, but the distance is smaller, and so the attraction wins, and that paper will get sucked up to the comb. Okay. Same thing that happens with the balloon, right? When you rub a balloon on your head, we'll make this one pink, right? The balloon gets negative charges from your hair. And then when you put it up against the wall, what happens is as that balloon moves to it, the wall is not is neutral. The wall is neutrally charged. But what we get is we get some polarization, right? We get positives end up lining up over here on the wall, and the negatives get repulsed away, and so the balloon sticks to those positives that are closer to it. Okay. So again, these molecules that are electrically polarized, right? They have a little bit of negative on one side and a little bit of positive on the other, kind of helps out the world. Okay. Um, water molecules, for example, are what the term is. Let's see here. Is called an electric dipole. When one side of the molecule is positive and the other side is negative, that's called an electric dipole. Okay. Let me just draw that water molecule for you real quick, just so you can see. So that's the oxygen part. And that's a little too big. Let's try that again. All right. There we go. There's a couple hydrogens. The hydrogens actually end up looking a little more positive. Kind of looks like Mickey Mouse. Sad. Okay, but that's an electric dipole. Okay, because one side is a little more positive, the other side's a little more negative. But that allows the next water molecule to line up with it, right? Again, with the positives, and this is what we call hydrogen bonding, because now the attraction here and here is strong enough to keep those molecules stuck together. And that's why water is quote unquote sticky. All right, so that is charge polarization and charging by conduction and induction. All right, we'll talk to you guys tomorrow. Thanks.